So, welcome to the last lecture on the module on verification. So, basically till now if you look at our course, we are in this module on verification, we were mainly discussing that given a system, how we can formally verify that the model actually behaves our desired intent. So, we started with the basic LTL and CTL based model verification. Then there we have seen basically the main problem which actually brings down the scalability issue is modeling the system in terms of state space. So, given a system, the way to model it is the major bottleneck. So, then we have seen how we can go for verifying large scale systems. So, one way of improving scalability is that you can use a binary decision diagram and use symbolic model checking. So, basically the idea is that instead of modeling explicit state space enumeration, we try to model using BDD. So, where a lot of redundant variables are eliminated, and then all our labeling algorithms, which basically is the heart of CTL and LTL model checking, we can easily do on the BDD itself. So, that is actually called symbolic model checking, which actually optimizes the verification paradigm from normal state space modeling to symbolic to BDD based model checking. So, where we can go from a jump of small scale system to somewhat large scale system. But then we have seen that if you really want to go for NOC or SSE kind of structures, bit level modeling will not at all help you. So, there we had an entire lecture on high level decision diagrams like arithmetic decision diagrams, high level decision diagrams, etc. But the problem there was that we do not have very good labeling and model checking algorithms on those high level decision diagrams. So, that is actually a way of part of research paradigm where people are trying to go for symbolic kind of model checking, not on BDDs which are at binary bit level or binary level, rather than on the high level models. But still, as I was discussing on that lecture also, that is not very well matured. Today basically we are going to see another way of optimization, that is actually called bounded model checking. So, what is the core idea? So, in case of symbolic model checking, what we were doing, we were at the gate level or we are at the bit level. In bounded model checking also we are at the lower level of bit level only, because when you are going for model checking, there will be labeling algorithms, so which we have not very well matured techniques for the high level diagram. So, when we talk of bounded model checking also, we are also at the lower level of enumeration. But in case of symbolic model checking, what we have seen, we have eliminated or handled complexity by using binary decision diagrams, so that redundant variables are eliminated. So, we have a lot of compression. In case of bounded model checking, we think of in a drastic other direction. So, in that case what we do, say for example, we have to find out a safety property that in all paths globally something should hold, like in all paths globally some safety property. Some safety property can be like you have a microwave, the heating is on, correct, and the door should be closed. That is safety property which should be verified in all these states. Now, if you are going AG, all paths globally. So, if you are thinking of all paths globally, that means you have to check that propositional and formula in all these states. But rather in bounded model checking, what we will do, rather than checking maybe for all long traces from the initial state, say, we are going to bound our search to a restricted set. That is, maybe if I say that bound is 2, in this case planning problems, we can reach the desired state in k steps. So, we put a bound that from the initial state we reach and try to verify the properties as given in the CTL or LTL formula, but we bound the search space or search length, trace of length k we are only going to search. So, what we are going to do? Basically, we are having an optimization by not searching the entire very long traces, where we are searching in a bound. What are the advantage and disadvantage? Obvious disadvantage is you are losing on the completeness, because there may be a bug or there may be a problem in some set which may be very long further down the line in the trace, but you will not be able to find it because we are putting a bound. But advantage is that we are going to handle larger systems, because now we are not searching for a very large state space. So, we not even model those long, or we are not even going to model the state space or transition relations at the further down the lines. So, there is some trade off. In case of BDD or symbolic model checking, we are only having an advantage that we are improving the complexity, but we are not losing anything because if you are modeling any system by BDDs, we are not losing any information, rather we are only eliminating the redundant variables. So, there is no loss in any kind of completeness or correctness, but here we are going to lose on that ground basically. But anyway, the idea is that for most of the general cases, you find the bugs very early. It is a very rare case that the bug will be something 10,000 states down the line. Rather, it is very probable that the bugs will be found in the states which are having shorter trace length from the initial state. So on that core idea, bounded model checking is standing. And one more thing before we start, basically bounded model checking generally works in a counterexample idea. So what is the counterexample idea? I will give you a basic gist. Like we are saying, for all paths globally, some formula phi should hold. That is a safety property. As the example I have given you, microwave is running, that is heating is on, but at the same time the door is closed. So the safety property should hold everywhere. All paths G. So now in this case, even if you are going for bounded model checking, for all paths of length k from the initial states, you have to verify. But I can do a slightly different way. Just think about it. There exists a path where in future not of phi. That means what? That means you are saying the first safety property says that all paths if you take, maybe I have a bound, because you are talking about bounded model checking. So everywhere this phi should hold. This I am going to verify. So of course, whatever formula you develop, you have to search the entire space at least up to bound k. But if I just think of a counter example, if I can somehow find at least one path, maybe say this one, where in future, but here also as I told you, bounded model checking means future cannot be infinite. There is a bound on the future. That is what is a bounded model checking. If I say that in all paths in future, so basically in a normal model checking sense, the future can be infinite. But in bounded model checking, we restrict the future length. So what we will try to see, if there exists a path where in future not of phi. That is, if there is a path, say from the initial stage, a path of length k, because our future is bounded by k, where some state is having not phi. That means what? That means there exists a state in the system within length k where phi is false. That means obviously the safety property does not hold in all these states. So that means this is a counter example which you need to debug. So therefore, the idea of bounded model checking is that rather than checking the formula directly itself, we try to find out the negation of it, and then we try to find out that this is the counter example and we try to work upon it. So finding a counter example is better because that will tell you where the bug is, you can recover, and the counter example basically always translates from all paths globally, all paths in future to existential quantifiers, so that you can have to just search in one path. So that is the basic goal of or idea of bounded model checking. Now which we will basically see in details. So before, when you talk about like symbolic model checking. So what is the idea of symbolic model checking? You should know about binary decision diagrams. All the labeling algorithms or fixed point computation are on the BDDs itself. But when you are talking mainly about your symbolic model checking, we do not use BDDs. We use satisfiability of Boolean expressions or Boolean formulas. So just I will give you a gist what is a Boolean formula and why it is satisfiable. So you all know what is a Boolean formula. The variables are Boolean variables, and then you write a function in terms of them. So there will be and or of this Boolean or the literals as we call. So basically the formula where there will be binary Boolean variables, and all the Boolean variables or the literals basically will be having the relation of and or. And basically we call it satisfiable if and only if there is some assignment on the variables which will make the function true, that is equal to 1. Like for example, as simple as that, if I say x plus y. Okay, then satisfiability means x equal to 1, y equal to 1, the function is basically 1. So we can say that this is a satisfiable function. Or if you have something called x dot x bar is a unsatisfiable expression, because whatever value you select, the final answer will be a 0. So there is no satisfiability values. So this is standard SAT. I mean, if you want to read more details, you can take any foundation of computer theory textbook, you will be able to find out. Here basically, but whenever we will be talking in terms of SAT, we generally put it in a normal form, CNF, we call it the CNF form. So in CNF form what happens, we have some clauses like say omega 1, omega 2, omega 3. So in each omega you have some of the variables, we call it as literal, like B or C, not A and not D, not B and not D. So this will be there, and all these clauses will be basically having a AND relation, omega 1, omega 2. So the whole equation to be true, what should happen? Each of the clauses should be true. That means this one should be true, this one should be true, this one should be true. And how the clauses can be true? If any one of the literals is true in that, because they are all connected by OR operation. So if any of them is a true, a literal is true in a clause, then the whole expression. So if one literal is true in a clause, then that clause is true. Now if all clauses are true, your final formula is satisfiable. So for example, here if you see that we have a satisfiable values, a equal to 0, b equal to 1, c equal to 0 and d equal to 1. So let us put it a equal to 1, b equal to 1. So if b equal to 1 means 1, so this becomes true. Now a equal to 0, so not of a, so this is becoming 1, this literally is true. Then basically we have d equal to 1. So d equal to 1 means by virtue of this is equal to true. So as all the clauses are true, the formula is satisfiable. So we call it as a assignment, or the expression is satisfiable. One thing I have to tell you at this point, this problem is known to be NP complete. So, I mean, you cannot have, nobody knows about a polynomial time or an easy algorithm to solve it. But there are a lot of heuristics basically which can tell you if there is a satisfiable set of Boolean solution to that, it will be told. Otherwise, if there is unsatisfied, will not also report that. But as already told, they are heuristics. So, what are the disadvantages of heuristics will always be there. They will give you the solution very quickly, but that may not be correct. That means in many of the stray cases, even if it is satisfiable, the heuristic will say that is not satisfiable. That may basically happen. But as it's an NP complete problem, if you are going for exhaustive enumeration based solution, the time taken to solve a SAT will be very, very large. So, there are a lot of heuristics available to solve to find out whether a Boolean formula is satisfiable. But in fact, that is actually an entire full series of lectures should be there to know about heuristics for satisfiability. Just like we had an entire series of lectures on binary decision diagram, how binary decision diagrams can be used for model checking, all these things we have done in details. But in case of satisfiability, we will just restrict to what is the satisfiability problem, how verification problem or bounded model checking can be modeled in terms of SAT, and then we will give you directions of how to solve satisfiability problem using some exhaustive algorithms, and then you will give reference where people will be telling about the heuristics, because there are lots of heuristics to solve it. So, this heuristics for satisfiability is not a part of the course, but rather we will try to show you how SAT can be used for model checking rather than bounded model checking. But given a SAT in normal form, CNF basically we call it, how people can solve it using heuristics, you can read up with the basically the references given in this course. So, as I was telling, I was just depicted in this slide. So, you can see that explicit model checking 2 to the power is the maximum size. I rather call it even less, that is by explicit state modeling. So, it is the size can be very, very less, 2 to the power 10, even I sometimes say that even 2 to the power 15 is also sometimes very large to do this. BDD or symbolic model checking is 2 to the power 120, so it is order of 2 to the power 120. So, it is quite high, but still not as high as I should tell you should be able to verify NOCs and SOCs as a whole. So, what people try to do, people modularize and go for distributed verification, and several other distributed techniques are available, or somebody goes for that I will explicitly verify all the blocks and then try to see the interfaces, etc. So, there is another set of literature to see how they can handle such big systems. But another direction which we have seen in this work, people have tried to model the very big systems in terms of basically other type of decision diagrams like high level decision diagrams or arithmetic decision diagrams, and try to formally verify on those high level BDDs you can tell. But again, as I again repeating that model checking as smooth or as available for bit level BDDs are not available in case of those high level diagrams. So, still people are thinking about it. So, at present BDD can give you a model checking for in the order of 2 to the power 100. Bounded model checking is slightly different. It can give you in a higher set you can verify, larger systems you can verify, but mainly people are trying for safety and liveness properties. These are the two properties which people have been able to verify in bounded model checking with targeting very large systems, because safety, as I told you, you just try to verify whether some formula holds in all these states and then you negate it, and then you are trying to find out whether there exists a path where in future that formula which is for safety is false. Liveness basically it tells all path in future something happens. That means I can tell you that in all paths in future this will happen. An example is I send a request, in future the request will be granted. So, this is some kind of a liveness property. So, what do? You say that in all paths in future some property will hold, but here as I told you the future is actually restricted by a length, but still you have to verify in all the paths. So, what people try to do, they try to find out a counterexample. So, what is a counterexample? There exists a path where globally, actually maybe you can call it phi, then it will be phi bar, not of phi. So, that means what? If there exists a path where all the states phi is false, that means that means basically if I say that there exists a path where globally phi is false, that means phi is not true at any place, then obviously there will exist a path where in future phi is not going to hold, because obviously it says that is a path in where all states, if you see in future this phi will be holding. But I can find out that there exists a path like this where in all these states it is not phi. In all these states it is not phi. So, of course, this not phi trace will actually say that it is the liveness is violated. So, that means this trace is giving the counter example for liveness. But again, as I told you, we are always restricted by length. Yeah. So, whenever we say that globally or in future, we will just search our limit by k path length. So that will actually have the problem on handle larger systems, because we are truncating or cutting down on the length to be searched. So basically, as I showed, both safety and liveness can be explained in terms of a counter example, where from all paths you can find out there exists a path. So we will be searching only in some existential paths, and also that also with a limited length. So therefore, so far safety and liveness are very well studied in bounded model checking, or if you want to apply bounded model checking, safety and liveness properties can be verified with very low complexity even for larger systems. For other properties generally means there is a lot of other ways to handle them. So for the time being, it is easy to understand and very obvious, as I have given you, that bounded model checking works on a counter example. Like all paths in future is a liveness property, we will go for the negation, we will find out that if there exists a path where globally this property is not true, that means you are going to find out a counter example. Safety means in all paths globally some safety property should hold. Here we are trying to do is that we will find out that if there exists a path where in future not phi. So in that case, basically there is a path where in future this phi is going to be a false, so safety will be violated there. So that is a counter example, but everywhere in future is restricted by a limit. So therefore your complexity is handled. So that is what is the idea. So in that way bounded model checking works very well for safety and liveness property. So basically this is just a repetition of what I am saying. So the main problem of BDD is the reachable state space, which is quite large. So in case of bounded state model checking, we restrict the reachable state space. So in OBDD or symbolic model checking, the property is evaluated recursively by a fixed point computation on the reachable state space. So in BDD, the reachable state space in the entire system, but in case of bounded model checking, the reachable state space is restricted by the bound. So it actually helps us in solving it. So in bounded model checking, obviously the OBDD modeling of the system is the problem. So because we are modeling the entire system by restricting the number of, by removing redundant variables. So it's a betterment from explicit state space modeling, but still OBDD models the entire state space. Advantage is entire completeness and correctness is guaranteed. But in bounded model checking, we basically restrict the state space search by some bound k. So it actually gives a solution to a level, because as I told you, we expect bugs to happen within a limit rather than postponing it, rather than think that the bugs will happen much later and not appearing earlier. That is a very rare chances. So we take that assumption on the liberty and try to give you a very low complex solution to handle larger systems. So that is the trade-off basically. So the idea of bounded model checking as written formally in terms. In bounded model checking, we construct a Boolean formula that is satisfiable, that is the SAT we have already told. If and under if the underlying state transition system can realize a finite sequence of state transitions that reaches certain states of interest. That means what? We are bounded model checking means one side there will be a Boolean formula which will be actually modeling this one. So that is why there is an if and only if condition is there. So for each of the system we are modeling, what you are trying to verify? We are trying to verify whether a sequence of trace transitions. Generally in this case we try to find out existential path. There is one path of state transitions which reaches certain states of interest. That means where the phi is not true, phi is false. That is the states where basically we want to look for the formula under question. So that is, given our system, we are not going to model the entire state space or reachable state space. We will rather restrict it and then try to model it in terms of Boolean formula, such that if the Boolean formula is satisfied, if and only if you are able to reach that search space or restricted state space, that interested formula in picture. That means maybe I am having single trace. Just assume that I am taking an existential path, some that you are trying to verify liveness by a counter example. Maybe I want to find out that here this phi, rather not of phi, whatever you want to verify, basically holds in this. So I will try to write this expression, the transition relation and the formula phi, because I just need to know that there is a transition relation and basically in all these states what is the formula that happens. Maybe here maybe phi may be true, here phi may be true, here phi may be false, here also phi may be false, or some other formulas may hold or not hold in any of these states. That we will try to represent in terms of Boolean formula, and also the state transition relation also will write in terms of Boolean formula. Now basically what bounded model checking will be, the formula is written in such a fashion so that if basically you can reach a state within the bound where basically wants to need to verify phi or not phi, what is of interest. If you can reach that state with the required formula in place, then only the Boolean formula will be satisfied and vice versa. So that is basically the idea of bounded model checking. State space, path of interest, you try to express in terms of Boolean formula, and such that if you are able to reach a state which is of interest to you, then only the Boolean formula will be satisfied and vice versa. That is what is the idea. Now with examples things will be more clear to you, but because this is a very abstract statement. So what we do, there is a propositional formula and bounded model checking. Basically we have a state transition system, that is your system. We have a temporal logic formula, sometimes propositional formula, which actually by temporal logic formula, which we want to verify. Like in safety, as I told you, given an example, microwave is on and basically your door is closed. And there is a bound, that is very important, that you are going to search to a bound. Then we actually model the relation in terms of Boolean formula. How you do? I naught S. This is because is the characteristics function of the initial state. Very simple. Maybe if there are two variables A and B, so there can be 4 states 0, 0, 0, 1, 1, 0, 1 and so maybe we can say that 0, 0, that is not A and not B. So this is the characteristic function of the initial state 0, 0. And then basically we are having a transition relationship, that is from Si to Si plus 1, how we are moving around it. So this is actually going to give you the unrolled relationship, but how long you will go? You will go from 0 to k minus 1. The transition relation will be only maintaining up to path length of k, that is the search you are doing. So that is basically the way we are taking a system and modeling in terms of Boolean formula. With examples it will be more clear. So we are having a CTL formula. There exists a path where in future some p, where in future p. That means basically it has come from the negation of some safety property. Like in safety what we have, maybe we are having there in all paths globally, assuming that not p. This is a state. We are assuming that not p is a formula which is required to be satisfied. Some properties, negation should be there everywhere. Like for example, formula is that heater is on and door is open. That should not hold anywhere basically. So heating on and microwave door open should not be holding anywhere. So maybe all paths globally not of p. So that is the thing you have to satisfy for global understanding, global correctness of the system. But again I told you, searching the entire space and writing in this Boolean formula will make it very large if you want to quantify every path. We will just try to see the negation of it. That means if there exists a path E where in future P is there, that means that is the negation of the safety formula. There exists at least a path where in future P is going to be true. That means if this holds, this is never going to hold. That means basically this is a counterexample. That means there is a path where in future at some point of time basically your safety property is violated. So you are interested only in that part because that is actually your counterexample. So that is why we call it EFP is basically a counterexample which you really want to verify in bounded model checking for safety properties. How do you write it? Here k equal to 2, mind it, so we are searching 2. So I naught S is basically your characteristic function of the initial state. Then the transition relation S0 to S1, S1 to S2, that is the two transition relationship because k equal to 2. So this part will represent the transition relationship, and very important is that because you are having S0, S1 and S2, this is one part, right? And then basically, so these first two clauses basically is telling you about the initial state and the path length. But now if you see PS0, PS1 and PS2, basically I am trying to find out that some property P, it can hold either in S0 or in S1 or in S2 because in future, so any state if it holds, your job is done basically. So that is what I am trying to find out, that P of S, P of S1, P of S2, that is whether P holds in this state or this state or this state. So the third clause basically is going to represent the temporal formulas truth in each of these states. So therefore initial state should hold, the transition relation should hold in the Boolean formula, some assignments, and basically any one of these states should have the truth of P. In this case you can then verify this formula is true or a counterexample has been found. So this is the idea. We try to take a CTL formula like EF or EG, and then we try to basically, as I told you, we will be mainly talking about E of P and E of F and E of G because they are counter examples for safety and liveness property. So we can say that here in this case we are trying to see that in any of, because it is in future, so we are trying to see if in any of these states the formula is to be checked, temporal formula is valid. So in this case we will get a satisfiable explanation. Theory, better to take an example because always from my understanding actually if you compare testing and verification is a more mathematical problem or more involves more of theoretical concepts in computer science. So always better to explain with example. Simple 2-bit counter, as you can see 0001 1011. State encoding tuple is L and R. So initial state L0 and R0. Done. Now I have to write the transition relation. So as you might have seen in your symbolic model checking, we had something called x and x prime. So x was the state variable corresponding to the present state and x prime was the state variable corresponding to the future state. So if you have, say for example, if I want to model 0 0 to 0 1, so you would write x, not x and x prime. So that means you are going from 0 to, you are going to write it as, sorry, we are turning in terms of L and N prime. So maybe L is the next one, so 0 to 0. So it is will be not of L prime and L prime and not of L. So we are using this one to, this negate symbol we are used to represent is the negation of a variable, because prime is used to generally represent the next state. So this was already seen in the symbolic model checking. So we will write it as not L, not of L prime and not of L. So not of L. So that means it will be basically representing from 0 to 0, the MSB. And also you are going to have, see, this one is 1. So basically it will be R prime and not of R. So basically L, not of L and L means it is coming from 0 to 0, and because this one we are considering as L prime and R prime next state, and this is L and R. So basically, and this one is from R prime to not of R. So not of R is this one and R prime is basically 1 correspond to. So this transition can be captured in this form. So this is we have seen in symbolic model checking. But in case of bounded model checking, we will be using this one as well as another way of representing, which I am going to see. Just concentrate on this. Actually, this will help you to represent the formulas in a smaller, compact fashion. So you need to look at it. It's very interesting. You can see that this LSB is 0 if and only if previous both of them are XOR is to be 0. Like in this both are 0, so 0 XOR 0 is 0, so you are going to get a 0. This one if you take 0 and 1, XORing is a 1, so you are going to get a 1. Now 0 and 1 if you are XORing get a 1, so the MSB is a 1. Now 1 1 XOR is a 0, so again you get the MSB as a 0. So MSB can be very easily represented by the fact like L plus 1 if and only if Li XOR Ri. So in this case, in the case of symbolic model checking, we were using prime notation. The next stage was represented by prime. But here in this case, the same thing is represented by I plus 1. I is the previous state, I plus 1 is the next state. Because in case of bounded model checking, you will have 1, 2, 3, 4, 5, 6, 7, 8, 19. But in case of symbolic model checking, we only have present state, next state, present state, next state. So x prime and x prime and x, y prime and y would suffice. But here as you are having a length, and the length is bounded by k, so you are using the terms Li plus 1, Li plus 2, Li plus 3 like that, instead of having a prime notation. Along with that, but that is not the issue, we can have a prime notation or a non-prime notation, because prime actually implies Li plus 1 and non-prime implies Li. But if it is a chain, then actually you should have Al, L prime, L double prime, L triple prime like that. To avoid it, we are putting a lower index. But other thing is that basically we are writing it in terms of basically if and only if. So we can also use this relation, like characteristic function is L naught R naught, that is both of them are 0. So as we can also use this way of writing the states like Li plus 1 and Li plus, means we can write in the symbolic model checking manner also, like Li plus 1 in this case not, and then Li also is not, because both of them are 0. And also we can write it in terms of like this one as this value is R, so it is Ri plus 1, that is equal to 1 over here and not of Ri. So this way you can also represent this way. Instead of prime and double prime, you can put I as the indices. But there is another way of writing which I am showing over here, because then it will be more compact, because in case of if you want to write it in this way as I have shown you for symbolic model checking, then you have to model this, all the 4 you have to model in that fashion. Another way of doing it is that the observation I have showed you, that the MSB basically is 1 if and only if the previous state bits are XOR to be 1. But and the LSB, if you see, they are toggling 0 1 0 1 0 1 and 1 0. So this one is 0 1, then from 1 to again 0, from 0 to, so is toggling. So therefore another way of writing this expression, both way are similar, the way of symbolic model checking as I have told you, or in this one. So it is saying Ri plus 1 is equal to Ri. That is a generic expression, that if you negate the LSB, so you are going to get the next state R, next state value. And the MSB, whatever the MSB of the next state is actually the 2 bits Li and Ri of the present state, and you XOR it. So this is another way of writing. These are if and only if statement. So this is another way of writing. So in bounded model checking, you use both the way of writing, so that it becomes more compact to represent, but actually they are all equivalent. So you can write either in the symbolic model checking fashion, but instead of putting R prime, R double prime, R triple prime, you better put the indices. or you can write in the if then else formula. So both of them are same, we will see. So basically till now if we concentrate on, forget about this way of writing the expression, assume that this is a valid one, both of them are correct. So you can see I naught L0 R0, that means basically it is the characteristic function of the initial state, and next state LSB is basically the XOR of the 2 bits of the present state, and the next state that is equal to Ri is not of Ri, present state LSB, if you XOR you are going to get the LSB of the next state, as we have explained. Now importantly, now we are going to see that how we are going to model a property using bounded model checking and how we are going to do it. That is very important. Now we have to pay a lot of attention. We are having something called all paths globally. All paths globally, some formula. What is that? What is the formula saying? The formula is saying that not of L and not of R. There is some formula globally, this should be true. That is, in all paths globally, either not L or not R. That means in no state you can have state 1 1. If there is a state 1 1, the safety property is violated, because the safety property is either not L or not R. That is, either of them should be basically 0, but both of them should be 1 is not a safe state. So you have to find out that whether this property holds or not, and the limit is 2. Interestingly, if you see, so only this state is having a problem because both of them are 1. We are starting from initial state. So bound space is only 2. So in this case, you are going to say that the formula is satisfiable. But if you make the search space 3, it will be a non-violation, because it will show that no, this is the state where it is violated. So that is the idea of bounded model checking. Sometimes it may give you a incorrect answer, because here in this state it is not valid, but we are assuming that we can search up to 2 and our job will be done, because as I told you, we are assuming that the bars do not appear very long. So in this case we are keeping the bound as 2, so of course you are going to get an incorrect example. But then what we are going to write? We are going to try to find if there is a state, there exists a path where in future negate, that is L and R. So that is what is the problem, both of them 1 1. So if there is a state where in future, if this is going to be true, bound is again true, then actually we are having a case where the safety property is violated. So we are not going to search this. Basically we are going to model and search this, and if we find it is satisfiable, then you know that the Liveness property, the safety property is not true, and there is a counter example. So the counter example is basically this state. But we are not going to find out in this example, because we are going to take the case of 2. Then we will see if we make it 3, then your problem will be solved correctly. Then you will be able to find out that there is a state where this safety property is violated. And so basically now we are going to do is that we are going to find here exists a path where in future L and R, L and both of them are 1. So how do you write it? So if you look at it again, pay attention, S naught. So basically if you look at, this is the not L naught and R naught, that means it is basically your characteristic function of the initial state. State transition 1 and state transition 2, from S0 to S1, S1 to S2. So L1 is nothing but the XOR of L0 R0, and R1 is nothing but not of R naught is not of R1. Already we have seen this in the last slide. Similarly for the second transition we can model it. Now you see, so basically what we have done in this first clause, this first set, basically the first one anyway is initial state, the others two basically models this transition and then this transition. Next what? So these are the two transitions modeling this, these are the two expressions, T transition relationship of these two transitions we have shown. Now we just need to see that whether both of them L0 1 1, L1 L0 R0, both of them 1, are they both of them 1 in state S0? This formula is going to capture the fact. L1 and R1, are they 1 1 in state S1? This formula is capturing that. And S2 means L2 and R2, are they 1 1 in state S2? So this one is actually going to capture the fact that whether the safety property is violated or not. Now how to find out satisfiability? So we are going to see whether it is satisfiable or not. If it is 3, we already know it will be satisfiable, but in this 2 it will not be satisfiable, and in fact they are giving a wrong answer. So anyway, let us not at the present think that it is a wrong answer, because we can visualize this, but in formal sense nobody can, it's a long system, so nobody may be able to visualize it manually. So we will assuming that in this case it will be true, that is no state is having the value 1 1. So the global property, that this property in all paths globally not of L or not of R is satisfiable. That means we will not be able to find out any counter example. Not finding any counter example will imply that this formula is basically true. So let us try let us try to find out some, because they are all Boolean variables, you have to find out some satisfiable operation. So of course, and everything has to be individually true. This has to be true, this has to be true, and this formula you can find out. So let us try to find out 1, 1. So obviously, if this has to be true, there is only one way you can do. L0 and R0 should be 1, 1. Otherwise, this clause will go away. Fine. So if I put L0 and 0, 0, then of course I have to put L0, R0, 0, 0. So in this case, this one is not going to be true. That means basically we have to now rely on L1, R1 and L2, R2. So then this is mandatory to put 0, 0 to make it true. So I have to make it a 0, 0 here. Now you can also find out, you'll be able to appreciate the fact that basically this one is already 0. L0 is 0, R0 equal to 0. So this is also equal to 0. In fact, that means equal to 1. Negate it, and this one L0, R0 means basically it is a 0. That means L1 equal to, because you have to fix this, because not L0 and not R0 means both of them has to be 0, 0, means L0 has to be 0, R0 has to be 0, so that this clause becomes true. So that is fixed. Now if you fix this, then this one is becoming 1 and L0, R0 becoming 0, so L0 is equal to L1 equal to 0. So L1 will be equal to 0 and R1 will be equal to 1. So even this one is also not satisfying, not becoming 1, gone. Now only one thing is remaining, the last one. So if you calculate, this one will be 1 and this one will be equal to 0, because this R0 is 1. So this one is basically equal to 1, not of R1 means basically it's a 0. So 1, 0. Again this is 1 and this is 0. So basically in no way you can actually satisfy this clauses together, because it says this or this has to be satisfied. Because this I can do. If I put L0, 0, R0, 0, and the assignments I have shown you can easily satisfy these three clauses. But here in none of the state S0, S1 and S2, you can have the value satisfiable, because it is 0, 0, 0, 1, 1, 0 is not satisfied. So therefore it will tell that this is a non-satisfiable Boolean formula, and therefore no counter example has been found. So your job is done. So you can say that this is the property holds true for k equal to 2. But now as you see, as we have already seen, this is a wrong answer, because we are taking a lower bound. So what I have to do, I have to increase my bound to 3. So in this case, of course, it's an homework you can try out. There will be another expression called T of S2 to S3, and then this one will be equal to L3 XOR L2 XOR R2, right? And then it will be R3 equal to XOR R2, not of R2. And in this case, we will have another one. So this one will be OR, and the P of S3 will be equal to L3 and R3. So now you can easily find out that this will be satisfiable, because if you put 0, 0, you are going to get the answer 0, 1, 1, 0, and the final will be, this one will be, L3 will be 1, 1. You are going to get it, and then obviously this is false, this is false, this is false. But basically L3 and R3 both of them are 1. So this clause will be making, because these are all odd, if you see this and these are odd. So this one will be true, making this entire set true, and of course there will be a satisfiable assignment. Just you can calculate in your home and you can find out. So if I make k equal to 3, so these clauses will change and you are going to get a satisfiable assignment for the counter example. That means that is going to tell you that this path basically is a counter example, and then you can debug and find the answer. Okay, so done. So that was simple. So we have shown with an example how basically we can handle the so-called your safety property. Now we are going to see the liveness property. So what is the liveness property? So one thing I should tell you, that this Boolean satisfiability check I have done manually, like putting 0, 1 and so forth. But in a general case, it will be a formula in CNF form, which I will discuss shortly, and then there are automatic solvers to do it. Mainly exhaustive solving is an NP-complete problem, so there are heuristics. So this do not go by this notion that I have done it manually, so it is possible to do it manually. For large case, there has to be an automation. But anyway, so now I am going to slightly change, because we are now going to see the liveness property. So what I told you, so liveness property means here what they are requiring in all paths in future L and R. That means they want to say that there should be all paths, if you take from the initial state, in future you should have the value of 1, 1 in the state. So if you look at this example, of course it is true. If you take any path in future, you are going to get this, which is going to be a true. But here we are actually slightly changing the example. Here I am putting a loop, same counter, but I am putting a loop over here. So the formula will be false. Basically because I go over here, I go over, there will be a loop. So in all paths in future, you are not going to have the value 1, 1. And again bound I am taking as a 2, you can take 3 or whatever, as I am going to get the gist of it. So now, fine, done. So now basically how I told you, how will you solve it? So I told you that we will have to take, there exists a path where globally L and R negate. That means there should be a path where in all states 1 1 is false. Of course it is there because you can go over here, and there is a loop. And one thing I should tell you, I am not going into more details because that will make the things very complex, that when I am saying states of size 2, length of size 2, path 2, basically this loop I am not going to count explicitly, because otherwise it will make the problem entirely long, because it is an infinite loop, so your bound should be infinite. So to keep the thing simple, I am not going into the formalities. Basically, I am not going to formal analysis of this, but just keep the gist idea or quote unquote idea in mind, that when you are looking for liveness, 1 length, 2 length, after that we are going to not explicitly count the loops. We are trying to see that, I will show you how to do that. Rather we will try to find out that there is a path, there is a path. And in this path, basically globally, this property should be false. That is 1 1 should be false. And also, as liveness globally means what? There should be a loop between these 3 states. That means in this case, in this state, globally this should be false. That means here also it should not be 1 1, here also it should not be 1 1, and here it should not be 1 1. And there should be a possibility that you cannot exit from these 3 states, or in any one of these states, or any 2 of these states. That means we have found a subset of states which we are calling globally with respect to bound 2. So in this case 1 and 2 is the bound, and you cannot, and in all the states within that bound, your property, that is 1 1 is false, and you should not be able to come out of this set of states. So it can be either there can be a loop from here to here, so that you will be looping in these 3, or it can also have the case that you can loop back from here, you can also have a loop over here. That means these are the 3 states which are violating this property, at least in a path, and you should never be able to come out of that path. So there should be a loop. So in this case you can find out the loop is in this one. That's also okay, because you will not be able to come out from this 3 states, any of the 3 states when the property is not true. So therefore it is true that basically in future you will never be able to find out, in future you will not be able to say that, you will not be able to reach this state. So liveness property is not valid basically, because we want that after some time 1 1 should reach, but in this path basically you will be looping over here and your job is gone, right. So let us see how do you write it and how do you do it. So again, I am not here, it will be similar, this one will be similar. The first set, this one corresponds to basically your flipping condition, and there is only one loop. So if you look at it, how this only loop from 1 0. So basically this we can write by the symbolic state transition enumeration manner. So it can be what? It will be Li plus 1 MSB and Li, correct? Because same loop, it is from 1 0 to 1 0. So Li plus 1 Li, and Ri also is same, so you will have not of Ri plus 1 negate and Ri. So this is the same thing which we have shown over here. So this shows that Li plus 1 and not of Ri, that means I have just swapped the position. So Li plus 1 and Li not of Ri plus 1 is equal to not Ri. This is basically you are just modeling this loop. So this part we are writing just a symbolic way of enumeration of these transitions, only instead of bars x bar, x double bar, x triple bar, basically x to x bar is the next state present state, we are just enumerating with the the subscript. So basically we are going to try to figure this out, that there exists a path where globally not this has to be true. That means 1 1 should not be true in this path. So we are going to find out a path called S0, S1 and S2, label is 2. And very important is this one, the last statement, there should be a part of the loop. So first one is the initial state, then we have a state transition relation, already we have discussed in the previous example. And as we are going to check globally, so there should be a way that you cannot come out of this, either from this state or this state or this state or any one of them. That means you should not be able to exit S0, S1, S2 or any one of them. So that is the idea. Now we will see how to model it. So I am not going to explain too much. This is the S0 is basically your characteristic state of the function, initial state. This is your first transition S0 to S1. So this one is the XOR relation for the counter, and if you look at it, I am adding this one L1 and not R1, not R1, L0 and R0, that is the self loop. But in this case it will be false because the self loop is not present in the initial state. Similarly, this one is from S1 to S2 and this one is from S2 to S3. This one is very, very important. You have to keep everything in mind. L3 R2 this one, and L3 not of R3 and L2 not of R2. That means what we have done, just keep this in mind. So what we have done over here, so we have a transition, this is from S0, S1, S2, and S3 basically is at present S2 only. Some state I am keeping hanging, just keep it in mind. So what are we are doing? This one is a transition, very simple. There is one transition from this. From S2 to S3 is a question of importance. There are two cases. One can be S2 to S3 where S3 is equal to S2, that is the loop itself, and another can be this one, right? Path, this can be a self loop as well as this can be a to the next state. So this one I am keeping it as a question mark. Now what I am modeling? So this is state 1, this is state 2, and this one is state 3. Basically to model this one. So I mean just as I have done manually, you can easily do it. If you just put it 0 0, that has to be done for satisfiability. You will just get it 0 1. In this case you will get it 1 0. In this case you are going to get 1 1, or basically you see, in this case this is not going to be satisfiable. This is not going to be satisfiable by any way. But in this case you can have L3 also as 1 0. That is very important, because I mean just by calculating you can find out. So if you take 0 0, basically you are going to get the answer here as 1 0. So I mean just I should not tell it like that. I mean just I will try to take it the other way. So 0 0, this one will be assigned 0 1, this will be 1 0, and this one is actually 0 1 1 0. This is 0 1, so the answer is next state basically is 0 1, the next state is 1 0, here this state is 1 1, and the ground states basically this is 1 0, this one, this L1 R1 calls for this clause, the top clause will lead to 0 1. If you are going by the lower clause, so it will be basically also 0 1. We will see how it is. Sorry. So that means basically it's a 0 0. And if you take these values by the first clause, it is basically 0 1, that is the next state. But if you are taking by this one, also there is a possibility you can have this 0 0, L1 0 and R1 0, both of them. Like where? Like for example, if I take L1 is equal to 0, fine. So I am going to get this as the answer. Basically it is showing that L1 XOR this one. So we know that both of them are 0 0. So if you take 0 0, the answer of L1 is a 0. So if you are going to get this as a 0, that means this is not going to true over here. Similarly, in this case if you see L2, if I take this clause, so you are going to get L2 equal to 1 and R2 equal to 1, just like the simple expression. And then in this case you can see R2 is basically equal to 0. So this is equal to 1, L2 is equal to 1, L1 basically is equal to 0 from this clause. So you can see this 0, so it will be 0. So if you just do a simple calculation, means just you have to do it, that's why we are setting up the values, which is very boring to do explicitly in the lecture. You will be able to find out that this has to be 0 0, this one will be satisfied, this one will be satisfied. In this case, I mean this is going to be satisfied, but S3 is basically hanging. The next slide will make this whole picture, what I was talking in a bit confusing manner, will be clear. But only thing you take in mind that all of them has to be true individually, and they can be true either by virtue of this or by virtue of this. The first one goes from this state to next state, and next one represents the self loop. Next if I go, it will be clear. So these last three already we have explained in the last case. In each of the state, the property you are interested in. So the property you are interested in is that this should be true, not L0, not R0. That means nowhere it should be 1 1. So that is obviously valid, because if any of the states you are having 1 1, then of course you see that it will, one of the clause will be false and there is an AND relation. So this one we know that 0 0, L0 R0, so this one will be true, and L1 is 0, R1 is a 1. So this is L1 is a 0, that means this one will going to be a 1, because L1 is 0, so not of L1 will be making it true. And if you look at this one, we know that L3 is 1 and R2 is equal to, sorry, L2 is equal to 0 and R2 is equal to 1 0, that is state S2, L2 1, R2 0. So in fact this one is going to be a 1 and this is true. So in fact just I am writing down the values which will actually make every state true, and all of them has to be true. In fact if I keep any of these values as 1 1, if you check, each of these clause will be false and we are going to get the answer as a wrong. So to make it satisfiable, we have to make R0, L0 R0 0 0, L1 is 0, R1 is 1 and L2 is 1 and R2 is 0. You can easily see that by making these two, this is satisfied, and by L1 0 will be satisfying this one, and R2 is not, R2 is 0, so it is able to satisfy this one. So in fact none of the states is 1 1, so globally everywhere not 1 1 is satisfied by these 3 states. So that means S0, S1 and S2 everywhere we are satisfying that none of the states have the variable values 1 1. Done. So these states are checking your properties of globally all states, the negate of the property is true. Now this is very important, which you have to think a lot. So what it is saying, so initially we have asked this one, this one is of importance. So this says that there is a transition from S2 to S3, and we have two ways of doing it. One is this first clause, if you see, it is saying that it goes from S2 to S3, that is basically in this case S3 corresponds to 1 1. Another transition, and the second clause if you see, it allows again S2 to go through S3, but in that case it is a self loop. That means the second clause will tell that S3 is nothing but S2. These are the two ways of doing it. But as we also seen as a clause for the liveness property, you should verify that S0, S1 and S2 you cannot leave that by means of a self loop. That means what? Then what is S3? Then S3 cannot be this one. So what are the viable choices of S3? S3 can be equal to S0. So in that case there is a transition, there will be a loop. S3 can also be equal to S1. In this case there will be a self loop like this. Also it can be, S2 can be S2 itself. That is S2 can be S2 itself. That means there will be a self loop, which is the true in this case. So you have to model it something like this. That is S3 is nothing but S2. In this case the transition is something like this. Is something like this. Correct? Then basically like this. Then in this case S3 is equal to S2. Correct? And also there may be a case like self loop. So therefore the first clause here, it is telling that basically S3 is equal to S2. That means this is self loop. That means one, L0 equal to L3 and R0 equal to R3. So this is modeling the fact that S0 is equal to S3. That is this one. The second one, what it is saying? This one. So how it is reflected? L1 equal to L3. That means L3 is nothing but corresponding to S3 is equal to L1 and R3 equal to R1. That means there is a S3 is equal to, sorry, it is S0, S1 and S2. I'm sorry. This we are telling as S3. Sorry. So the first one is telling something like this. S3 is equal to S0. So this one. Second one is saying any one of them may be true. Second one is this one, and third clause is a self loop, which is actually saying that S3 is equal to S2. Now any one of them should be true because the OR, you see that is OR. So in that case, in this case, basically this modeling of the loop, you will find out that this is going to be basically true. Satisfiability. So now I will start putting the values of satisfiability. You can easily check this. So you start putting it as 0 0 because the only way to do it. So if you do it, basically L1 will be 0 and this is equal to 1. In this case it will be 1 and this is equal to 0. Here it will be interesting. Again here again L3 in this will not be satisfiable because if you take this, L1 will be equal to 1 and L1 will be equal to 1. So I am not taking this one. I am taking that again L3 equal to 1 and L2 equal to 0. So if you look at it, because L3 equal to 1 and R3 is also equal to 1 0. So you can find, and L2 you already know as 1 and R2 you already know as 0. So this 1 0 1 0 will satisfy this. We are not targeting this. So any one of them will hold. So I am taking this, so I am going to get this. So please remember that I am taking L0 R0 0 0 has to be done for this. Then L1 R1 is this, L2 R2 is 1 0, and L3 R3 I am also taking as 1 0. I am not taking as 1 1 because I have a choice. Either this can be true or this can be true. But of course this one I cannot put a loop because it will make it false basically. So anyway, so these are the values. So in this case I am not taking this, I am taking this one. So now here if you look at it, basically this is always true I have put, and now you put the values of this one because what is L3 is 1 and R3 is 0. Okay, what is L0? L0 is 0, R0 is 0. So this clause is not verified to be true, not satisfied by this one. But any one of them will hold. So now if I put it as L3 as 1, R3 as 0, so L1 is 1, but R1 is 1. So again not verified. Here if you see 1 1 1 0, this is also L1 is 1, R2 is 1. So this equivalence is done and this one is true. So the whole formula is satisfiable. Slightly tricky, think, read the notes and work it by hand. So just in a nutshell, what is the values, and there are actually this will be written as, I will show you in the next slide that how you can write basically all the formulas I am showing you here. Like this one is already a CNF, but in this portions basically this if and only if, how do you write it in terms of simple Boolean and or operation, I will show you in the next slide. But basically what happens, just satisfiability will start with 0 0, then this I will be satisfiable because anyone or is there, any one of the two, this I will do it. In this case I will not do this, I will take this to be satisfiable, and then of course you will find out that here is again or of and, so this one will be not, this one will be not, but this one will be true, and in this case everyone is satisfied because it is a AND operation. So this actually shows that this is satisfiable. That means we have generated a counter example here where it loops and basically you are not reaching a state of 1 0 within a bounded time, and you are basically generating a counter example. That means you are saying that in all paths globally you will finally reach the state 1 1 is basically false, because here you are going to have where you are going to get stuck up and here this is a counter example. So this is your basically your counter example. So now what I have to do, you have to basically eliminate this. So if you are going to eliminate this, means this will be going out. So in this case this one will be going out, this one will be going out, this one will be going out, and of course anyway you have to keep this check on, and then you can study the satisfiability. But before that you try to make k equal to 3, because in 3 steps we will be reaching this. So try to, if you want to solve it, or you have to find out that probability property is true or not, then basically you have to eliminate this is the debugging, because the self loop is killing you. So you do this and then trying to find out whether this is true or not, but again you will be finding out the problem because length is this one, make it 3, and the whole thing you can do it and you will be getting the answer. Again slightly complicated, read it and do it one by one, the values you do, you will be able to find out. Now what remains? Whatever till now we have been doing, we are all solving it by means of what? We are solving it by means of, we have to model, we are modeling basically some temporal formula, and basically we are writing it in terms of some Boolean expressions. And these Boolean expressions basically we are trying to find out whether they are satisfiable or not. So this is already in kind of a and or, Boolean and or, but this is slightly if and only if I have to convert it into and or. This I will do, then you will have a Boolean formula, and then there are satisfiability solvers which will tell you whether there exists any Boolean variable values which make it true. If that is there, then that values you have to study, and if it is unsatisfiable, that means your formula you are going to verify is false, and then you have to act accordingly. So that is what now remains to be told, that what is SAT and how basically it solves this problem. But again as I told you, SAT is an NP complete problem, so exhaustive programs will give you the true solutions, but it's a very exponential problem, very difficult to solve. So we will have heuristics, and we are not going to study heuristics, just give pointers. But basically you should understand that given a CNF or a conjunctive normal form, basically how at least a simple method to solve it, so that you can get an idea of what is SAT and how can we do it. So what is a conjunctive normal form? We call it conjunction of disjunction. Therefore that is, we will have some ands over here, and all the clauses will have some Boolean variables or the negations, and there will be or. So the whole thing should be satisfiable. That means each of the clauses has to be true, and each of the clauses will be true if any one of the literal is true over here. So that is what is the idea. Okay, and then basically what I will show you that how do you write it. So there is a distinct way of writing the solutions. So basically if you have a formula like this, x or not of x1 and x2, how do I write it? Basically it is something written like this, and or a naught if and only if x1 and or of a1. That means this thing is whole represented by a1. So I am just writing it in terms of what we have recently written in terms of basically for this bounded model checking, the way we are writing the straight transitions. So we are using if and only if clause, on if and only if operator. So basically how to write it in terms of a pure Boolean expression, that we are just going to reflect you, so that because you know that SAT can solve this type of things, and this is not with if and only if condition. But how this translation can be done, that I am going to give you a gist. So I am writing this. So this one is the case. Now again there should be an and. So now what I am doing, so I am saying and is equal to not of A2. So and if and only if not of A2. And then what is A2? A2 is equivalent to X2 and X3. So this is how I have written this Boolean formula in this type. Rather, we are showing how they can be written. Rather, in case of bounded model checking, we write in this fashion, and then we have to translate it to this fashion so that we can go for a simple SAT solving, which basically works on such type of formulas. But we have shown that if this is satisfiable, then only this is satisfiable, and vice versa. That is phi is satisfiable if and only phi dash is satisfiable. That both are basically equivalent in that terms. So basically, so what I told you, that basically that is why this has to be phi prime has to be transformed into CNF. So if the CNF, so this can be solved by a satisfiability solver. So if you have, this is how we write about this transition relations in our basically your bounded model checking. We need to transform this, and our job will be done. So I'll just give you an idea for AND gate, and then you can easily extrapolate for others. So this is how we write AI equal to x1 or and x2. Done. Now how it is going to be converted into a Boolean CNF formula? I write it as this way: AI or not of x1 or not of x2, not of AI and or xi, not of AI or x2. Now you see how it holds basically. Let us assume that A1 equal to 1. AI is equal to 1, then obviously this has to be 1 and 1. So if I make A1 equal to 1, then by virtue of this I did not think about it, this clause is true. But when AI is 1, this guy is equal to true and this guy is equal to false. Sorry, both of them are 0, 0, false. Then to make this clause true, to make this clause true and true, you should have the value of 1 and 1 exactly. Otherwise, because these are all ampersands, then this will be false. So directly you can see that I have to have x1 equal to 1 and x2 equal to 1. Similarly, let us try to make AI equal to 0. So in this case, it can be 0, 0, 0, 1 or 1, 0. So immediately if I make AI equal to 0, this guy is becoming 1 and this guy is becoming, this little is becoming 1. So immediately this and this are true, fine. So I need not think about it, then AI is becoming false. Then only these two has to be turned to 1, 1. So these two taken together has to give the answer as a 1 to make this satisfiable. So how can not of AI xi or not of x2 is to be made true? They will be true always unless and until both of them are 1, 1. So basically this one is now holding. So I can easily translate this AND gate relationship if and only a way of writing to this. Then basically this is CNF. So all the terms we have written in this case, if you look at it in terms of this one, in terms of this relationship, in carry is an XOR, but for all gates we can have a similar formulation so that we can, the whole thing can be transferred into a CNF formula, and then you can, SAT can solve it for you. So again I am not going to discuss in details. So this is again for OR gate, and then this is basically for your AND gate. Similarly you can easily find out. That is, you have to write there all ampersand which are not written. So in that case, for this one will be reflected in terms, this one will be reflected in terms, and so forth. So now that is what is being saying, that each Boolean gate basically which you are writing in terms of this equivalent formula, we can write it in terms of some CNF Boolean normalized form, and then you can have an ampersand of and all this, and then the whole formula which had lot of this if and only if basically operator will be converted into a Boolean form function or the CNF. And then already we know the theorem, you can refer it. So this equivalent means if phi is satisfiable, if not, if and only if phi prime is satisfiable. So basically the idea is that you have to write, even if you write the relationship of the Boolean model checking, bounded model checking, even you are having these clauses, still we can easily translate them into the CNF form using these structures, and then finally we will give this 3 CNF form to be a satisfiability solver, and the solver will tell you if it is satisfiable, what is the values which satisfies it, and of course I have to tell you that there can be multiple values of the Boolean variables which can satisfy it. It will report you, and those you can use to check the counter examples. But if it is not satisfiable, that also it will tell that it is not satisfiable, then basically you will find out that the formula being verified is true and there is no counter example. Just a simple example. So basically if you see this, as I was discussing, this is the CNF. So these are the some literals and these are the clauses and these are satisfying assignment. So there are some standard definitions. As I told you, satisfied if at least one of the C's literals is satisfied, because in this block any one of the literal has to be satisfied. Conflicting. So conflicting if all of these C's literals are unsatisfied. That means if this is 0, then this is 0. Then both of them are conflicting, then both of them are unsatisfied. So this clause becomes a conflicting clause. And actually this one will make the Boolean, that formula, unsatisfiable because they are all ampersands. So it will be an this will be basically your non-satisfiable, it will become a unsat. So if you have a conflicting this, then this is unsatisfied, then everything will be unsat problem, because conflicting is all the literals are unsatisfied. There is one way that is called as unit. Unit means that at least one literal you have not assigned, any one of the literal is not yet to be assigned, and all others are conflicting. That means this one is basically unit, means it has to be true to make the clause true so that the overall is satisfiable. So unit means the last result, and unresolved means some of the Boolean variables have not got their values. Very simple example: x equal to 1, x1 equal to 1, x2 equal to 0, and x4 equal to 1. This is satisfied. Why? Because x1 is 1, satisfies the whole clause. Conflicting, because x0 is equal to 0, x2 is equal to 0 means this is equal to 0, and x1 equal to 1, so this is 0. So basically this is conflicting because none of them is true. So if none of them is true means this is as all the clauses basically are ANDed, so this will make it an unsat, non-satisfiable. So it's conflicting. Unit means what? You see this x3 value we are not clear of, but all others are false. This is 0 based on this, x4 is 1, so this is also 0. So the truth or the satisfiability of this whole Boolean formula depends on the truth of this, but this is unassigned. So basically this is called a unit. That means to make the formula satisfiable, x3 has to be 1 in this case. And unresolved means there are some variables like x3 and x5 whose values have not been given. So this is basically some definitions which you need to know when you will be looking at the SAT solver. Now what I am going to do? Now I am not going to go into any heuristics. Rather I am going to give you the worst algorithm, that is explicit enumeration, and we are going to see whether the Boolean formula is satisfiable or not. So in this case we make a decision tree, and each of the decision tree we go for a depth 1, 2, 3, 4, and each of the depth we try to basically give the variables some values like 0 and 1, and let us see whether it is satisfiable or not. This is the exhaustive algorithm, nobody will use it, it will blow up the complexity immediately, but still it will give you a picture that how SAT is being solved basically. So you are taking this 3 clauses and the values. So at x1 we are starting, so we are putting x1 equal to 0 at the level 1. 0 at the rate of 1 means basically we are making x1 equal to 1. So if you make x1 equal to 1, then basically this is going to be a 0. So I am making x1 equal to 0 at the level 1. So if x1 equal to 0, if x1 is equal to 0, so basically in this case this is going to be a 1, and so this is satisfied. You need not bother at all. And nowhere else there is x1, so I am very good. So I am going to the next level. So next level I am making this arbitrary choice, x2 equal to 0. If x2 equal to 0, then I am putting it as a 0, and this one is going to be a 1. So this one is satisfied. Now you can see that x3 has become a unit. So you have to make it absolutely equal to 1 to get the answer to be satisfied, so that this whole thing is satisfied. So immediately you will write x3 is equal to 1 at this level, and your job is done basically. So x1 equal to 0, x2 equal to 0, and x1 equal to 1 is a satisfiable operator. But this I am telling you is a very bad algorithm, and a worst case complexity will be always exponential, because you are trying to explore everything, and we are starting from the sequence x1, x2, x3. There can be other sequences like x2, x3, x2, x1, all combinations, all possibilities of permutation combinations has to be tried to find it satisfiable. That is why people use heuristics. But this I am just going to show you to know that what is satisfiability and what is the other algorithms to do it. Similarly, you can also start with a1 equal to 1, and then again you can get other satisfiable values. Why? As I told you that there can be multiple ways a Boolean function can be satisfied. This is one set, and basically this is another set. So here people started with x1 equal to 1, and then you can repeat it, you will find out the values. But life is always not very simple. You can always have some kind of clashes. This you need to do backtrack. Well, it's very obvious. I think you can also appreciate that if you take such a rudimentary kind of algorithm, of course you will have clashes, and again you have to retract, and of course this can make things exponential. So I am taking a new example with some added clause. So I will go with x1 equal to 1. So if x1 equal to 1 at level 1, so this is going to be 0. So immediately you have to make x4 equal to 0. So this will becoming 1. Then anywhere x1 is there, so x1 is equal to 1, so this will be immediately 0. Then we have make x4 equal to 1, so not an issue, fine, right. So now x4 equal to 1 we have done, so anywhere x4, no. So x4 is equal to 0, so this is 0. So immediately this one is 0, so immediately this one x2 is becoming an unit, so immediately x2 is equal to 0, right. So x2 is equal to 0, otherwise this one will become false. So if x2 is equal to 0, then immediately this is going to be 0, now x3 is going to be an unit. So if x3 is to be a unit, then x1 has to be made, of course we are saying that x2 is equal to 0, so x2 is 0 means this one is going to be a 0. So now we have two units, x3 and not of x3. So there two are units which are conflicting. So you are going to get a conflict over here. So these are conflict basically. So these are conflict, because this one will tell x3 is equal to 1, and if you make x3 is equal to 0, so the clause 4 will be unsatisfiable. There is a conflict, and so you have to conflict and you have to start the other direction. So other direction you can start with x1 equal to 0, and I am not going to illustrate again. So then again you are going to have something, and then this is basically a satisfiable operation. So basically if you do in this manner, it is going to lead to a very big tree, and everything is going to take an exponential amount of time in the worst case, and this is not going to solve anything. But this has given you an idea that if a CNF is there, then in a tree manner you can find out the satisfiability. And once it is satisfiable, those values will be given, which will act as your counter examples. Now, this is a list of lot of heuristics available, which basically can solve this SAT problem in a much lower complexity. But anyway, the drawbacks of heuristics will be there, but as I told you, generally for all such NP complete problem, the practical way of solving is heuristics. So this can solve this SAT problem for you in a much quicker fashion and more or less accurate. So you can have a very optimized solution for model checking of very large systems by bounding the length of search. Then again, there is a lot of question people ask whether BDD is good or bounded model checking is good. There are a lot of ways. Some people say that bounded model checking of BDD is of course very accurate, always correct and complete. But again, it says that we need to have a very good variable ordering, otherwise it may explode, because the size of the BDD always depends on a good variable ordering. And still people say that as you are still enumerating everything, it cannot go beyond state of to the power 120 as I have shown you. But for a real case, things are much bigger. But in bounded model checking, it says that it generates shortest counter examples, because we are interested to find out where the first place where the error is, and generally errors occur quickly. So why need to search the entire state space? So go for a bound and solve larger state space. So both have their pros and cons. So basically we tell that basically they are actually complementary approaches. So both of them has their own merits and demerits. But best thing we can get if we can have some kind of high level BDDs and we can do model checking on them at a very abstract level. Even Boolean model checking, as you have seen, is also at a bit level. So can we move to the abstraction level and try to solve all these problems? So this is a research angle which I feel all of you should pursue. As if you might be feeling in this course, basically as this is also the last lecture of this course, basically in this course we have tried to discuss about the CAD algorithms, which is traditional, and then we have seen what are the different optimization problems and how we have changed or modified this traditional algorithm so this complexity can be handled. But still, for many of the cases, we have not reached the desired level. Like if you take verification, we have not even reached the level where you can verify the whole SOC and NOC in a go. Basically because either you have to go by symbolic model checking, or if you are going for abstract diagrams, we do not have very good algorithms for model checking in those high level abstracted diagrams. So there are a lot of gaps. Similarly in the way of testing, similarly in the way of designing and all these things, we have found out gaps. As it is not an entire course in itself, it just gives you some directions in which you can pursue your research when you are doing for CAD algorithms. So traditional CAD is very well established. The optimization problems I have told you in this course, and also I have told how we are attacking them, and also the gaps that remains have also been identified in this course. Now we are actually also uploading lot of references, papers and directions. So the goal of this course, one of the more important goal of this course is that you please pursue or try to take the important problems which are to be solved in this optimization domain. Because when you are going for very large scale multi-core processors, NOCs, SOCs, and these things this size will be becoming larger and larger, and our algorithms are not actually at par to meet them. So a lot of optimization important problems remain to be solved. So in this course, we have just given pointers to them, and we request you that you take interest in this and try to pursue your research in that. So again, thank you all for attending these courses, and we hope that you will pursue research in optimization of CAD and CAD for digital VLSI design. Thank you from our side.